Hi class, welcome to Unit 4 Lesson 5, where we're going to look at Young's double slit experiment today. So today's learning goal is, by the end of it, you'll be able to demonstrate an understanding of interference in light with Young's double slit experiment. The success criteria: I know I have achieved this if I can describe in detail the contribution of Young in wave theory and interference in light with Young's double slit experiment. Analyze mathematically the destructive and constructive interference, solve problems related to the Young's double slit experiment, and apply learning to the daily life problems. So light is at times difficult to study because of its wavelength and some other factors we'll go over. So if light has wave properties, then two light sources in phase should produce a result similar to the interference pattern in a ripple tank in phase. Remember what we looked at there? Light should be brighter in areas of constructive interference and darkness in areas of destructive interference. So it's pretty intuitive and it should be very easily observable. However, many investigators in the decades between Newton and Thomas Young attempted to demonstrate interference in light. In most cases, they placed two sources of light side by side. They examined screens near their sources for interference patterns, but they were always in vain, and they were defeated by the exceedingly small wavelength of light. In a ripple tank, where the frequency of sources is relatively small and wavelengths are large, distance between adjacent nodal lines is easily observable. In fact, when we saw pictures of it, very clear, they come out easily observable. And so when it shifts, we can see it very well too. And when we phase shift, with the experiments with light though, the distance between the nodal lines was so small that we can't even observe the nodal lines. And sadly, there's another more fundamental problem. If the relative phase of wave sources is altered, the interference pattern is shifted, as we saw with the water ripple tanks. When two incandescent light sources are placed side by side though, the atoms in each source emit the light out randomly and out of phase, and there's no way to control it. So when the light strikes the screen, a constantly varying interference pattern is produced and no single pattern is observed. So the atoms are constantly emitting this light and there's no way to control it, because even if you're turning it on and off, anytime you'd think if you just control the phase like that, on off, two pulses on, one off, it doesn't work like that, because when it's on, even if you're controlling like that, it's emitting randomly when it's on. So when you're having it on, even the first pulse versus the second pulse aren't the same. So there's a problem with light and observing this way. So recall from last time we looked at the interference patterns of two point sources that were in phase, and we had constructive interference, areas of constructive interference, the red lines, and nodal lines of destructive interference, these lines. And then we had supercrest, supertroughs as well. So Young's double slit experiment, he was very clever in addressing some of the problems. So he had used one incandescent body instead of two, which addressed the problem of the random nature of two light sources. And he directed its light through two pinholes placed very close together. And so then what happened, we've seen what happens when waves go through apertures. And so it was diffracted through each pinhole so that each one acted as a point source of light. And so he was able to get two sources. He got his two sources of light coming from the same light source. So he was able to if it's coming from the same one, he didn't have two out of phase random light sources. It was coming from the same one. And so since the sources were close together, the spacing between the nodal lines was large enough to make the pattern of the nodal lines visible. And since the light from the two pinholes originated from the same incandescent body, the two interfering beams of light were always in phase, and a single fixed interference pattern could be seen on screen. And so the result was some really strong evidence, because if this was a particle source, it wouldn't really work the same way. This shows some significant evidence of, and we've seen, like, this is how waves really react. This is kind of the nature of how waves interact with each other and not particles. So some really strong evidence for the wave theory. So Young's experiment, it resolved two major problems in observing interference of light. The two sources were in phase, because before, using two different sources, there was no way to control them, and the distance between the sources was small enough that a series of light and dark bands was created on a screen placed in the path of the light. These bands of bright and dark are called interference fringes, and the light ones are the maximas, with dark are the minimas. And as you can see here in the slide, dark and light bright bands, maximum and minima. And so this experiment, now very commonly called Young's experiment, provided, again, really strong evidence of the wave theory of light. So if we look at a more graphical, lined out view of Young's double slit experiment, we have something very similar to our source 1 and source 2 for the water ripple tank, demonstrating waves, how they constructively and destructively interfere and act as waves. So we have that portion here that looks very much like this, except the two sources are coming from diffraction from the one source. And as we talked about with light, that was really important, because this is very clearly in phase, since it's coming only from one phase, or one incandescent light. So it was a very clever way of getting two sources that were in phase for something as random as the atoms in the light. And here's just a diagram from a 3D perspective of his two-slit experiment. It just shows a little bit from a 3D perspective of the experiment. So in the experiment, we saw light waves in phase emerge from the slits as two different sources. And although the waves spread out in all directions, we will look at three different angles of theta. So for the first one, we have theta equaling 0. Both waves reach the center of the screen in phase, since they travel the same distance. And so what do we mean by the 0 theta? The angle against this line runs, this red line that runs straight beneath the in between the two, and eventually meets at where they meet. So this angle with the flat line is 0. So that's what our theta is. And as we'll come to see, it also represents our relative phase, but you can't quite see it in this one as much as the next examples, but you can see that the relative phase between them is 0, just like our theta, because our crests are lining up, our troughs are lining up, and so they're going to be having constructive interference all the spots, right? So it's negative, and so they won't be destructive interference at all. And so we have constructive interference occurs, which is what produces a bright spot on the screen, which it happens here as they converge. And it makes sense, because the waves are constructively interfering with each other, so they're going to be making a stronger magnitude wave when they're in line like this. So when this theta is not 0, then we get a different type of interference. So when when it's tilted with this theta, the wavelengths, they have to travel an extra distance of half a wavelength to reach the screen. So the waves from the sources arrive at the screen 180 degrees out of phase, or pi radians, leading to destructive interference corresponding to nodal line N1. And so if we had our bright spot here, now we're having a dark line here because, as you can see, when they are forced to go upward, the waves traveling like this, they are, if you notice this dotted line here, it lines up with S1's crest, and it actually lines up with S2's trough. And so now we don't have crest and plus crest or trough plus trough. We have a crest and trough destructive interference, and that's why we get a dark spot in nodal line. And this is because their relative phase is no longer 0. It's in fact 180 degrees or pi radians, because one of them has been shifted, essentially shifted where the crest was here and the crest was here. It's been shifted this way, or we can say this way since they're infinite, the waves go same distance, but it's been shifted by a phase shift, and in this case it's 180 degrees or pi radians. And so because of this shift, we have the crests and the troughs overlapping now, as opposed to before when we had nice trough and trough, crest and crest lining up. Where we had constructive interference, we'd have a bright at theta equals 0, but this theta, we have a dark spot because of this relative phase change and phase shift. And so we have our nodal line n equals 1 here because of the destructive interferences at every single point, if you notice. So we get our nodal line. So now if we move theta even further up, from the center of the screen, we reach a point where the path difference is lambda now, as you can see here. And since now it's traveling even more of a distance, because now we're pointed up even further this way, and so now we're going, in fact, an extra half wavelength than the previous example. And since half wavelength put it out of phase destructively, if we put another, well, it's traveling another extra half wavelength on top of that, it in fact brings it back into phase. And now we're back to constructive interference, because if this was before and this one was our before, and we've just shifted it by a wavelength, now instead of this crest being lined up with this crest, it's just being lined up with this crest, but it's the same magnitude. So when it's shifted, we have just same example as the previous thing, because waves just go on and infinitely, right? And so you're just taking the crest in front of it and moving it back, and it's the same magnitude, so you're still going to have the same, it's basically the same situation as you had before, the same value crest over the same value crest, and same with the troughs. And so now we get a bright fringe at this angle, because we're having the same constructive interference setup as our first example. And so we're starting to see a bright line here, a dark line here, a bright line here, which is what we saw in the slit experiment here. And so as you notice, we're having patterns of constructive, destructive. We have a bright here, and a dark here of destructive interference, and then we have bright constructive interference, and then we're going to have a pattern, right? And that's what we saw in his stripe here. And so you can guess that certain angles of certain amounts of theta are going to give brights, certain thetas are going to give darks. And so we can come to a general formula to find which values of theta yield areas of destructive and which ones yield areas of constructive interference. And so for destructive interference, we can use this formula we've seen before. And if we just plug in n equals 1, 2, 3, 4, and we definitely know the wavelength, we definitely know d, and we just do sine inverse of this whole expression, we'll be getting different increasing or increments of angles where the destructive interference occurs. So say b. And then for the other path difference, we have this formula, sine theta m equals m lambda d, where m is 0, 1, 2, 3, and on. And as we do the same thing, we plug in these values, put 0, and we know the wavelength in d, and do the sine inverse of this formula, and then we plug in 1, and then get a value, and then we get 2, and we get an angle. And so we have multiple theta m's that increment slowly up the stripe. And so this way, by using both formulas, we can get which angles give constructive interference and which ones produce destructive interference. Since the dark fringes created on the screen by destructive interference are very narrow in comparison with the bright areas, because bright, they obviously show up better than the dark ones, measurements are made with those nodal lines. Also, sine theta is best determined not by trying to measure theta directly, but actually by using a ratio of x over L. And so we're just equating everything to xn over L. And so what are these values? Xn is the distance to the nth nodal line measured from the right bisector. So right here, it's just coming from the right bisector here to the point Pn. And the Pn we're very used to, right? We know Pn is the one measured from S2 and S1. And L is just the length of the right bisector horizontally until we get to Pn. So if we take this new formula and don't use theta at the sine theta because we said it's not as accurate, and we just use the xn over L and the n minus half side, we can find a separate value of x for each nodal line. So generally xn, if we bring the L over, it looks like n minus half times L lambda over d. And then if we have substitute for the first nodal line, we could have 1 in here equaling L lambda over 2d, and likewise for the second and third nodal lines, we get different values of x. So now we have, for each nodal line, we have the distance, this distance xn, and so we can measure the size of the dark spots more accurately. When we have the first nodal line and the second nodal line, then we can use it to find the size of it, and likewise for 3 and 2, and then 4 and 3, and 5 and 4, and on. And so when we want to find the difference between two adjacent nodal lines, like the third and the second, right, they're adjacent, 2 and 1 are adjacent, we're basically saying the difference between adjacent x's, let's take x3 minus x2, and we have 5L lambda over 2d minus 3L lambda 2D. And so these are the same, numerator and denominator. And so we're really just taking 5x minus, or 5 something minus 3 of something. And so we get 2L lambda 2D. The 2's cancel out, and we're left with L lambda D, or if you bring the L back over, lambda over D. And so, but for this, for adjacent nodal lines, we have this formula is true. Where delta x is interesting is the distance between adjacent nodal lines on the screen. And then D is the separation of the slits. L is the perpendicular distance from the slits to the screen. Our screen is here, right? Our L. And yeah, so this formula holds for adjacent nodal lines. And we can calculate the interesting value of delta x. So let's look at a problem. So if you are measuring the wavelength of light from a single color source, you direct the light through 2 slits, so just like Young's experiment, with a separation of 0.15 millimeters, and an interference pattern is created on a screen 3 meters away. You find the distance between the first and the 8th consecutive dark lines to be 8 centimeters. Which wavelength is your source radiating? So we have good information. We have the separation here, 0.15. We have our D. We have our L here. And then you are told that the distance between the first and the 8th consecutive dark lines is 8 centimeters. So that's not really delta x, but we can get delta x from that. So when we draw it out, we have our dark lines. And we said that the distance between them is 8 centimeters. And that we know delta x is between consecutive nodal lines. So 1 and 2, this is delta x as well. And so if we know each of these are equally spaced, and we count them, 1, 2, 3, 4, 5, 6, 7, we have the distance here, and we want to find the distance of just one of these. We're going to take the total distance and divide it by the equal parts, just like standard division, right? And so we take our delta x is equal to this total length divided by the number of equal spaces, 7, and we have 1.14 centimeters is our delta x. And so we want to convert this to meters, make everything consistent, because we're going to be working with this formula down here. And so we want to convert our D, which is in millimeters, so times 10 to the -3 conversion. And so now we have our delta x taken care of. We have our L from the question, our D from the question, and we want to find wavelength. And so we're all set to go. So let's rearrange for lambda. D times delta x over L. Plug in our values. We converted them, so they're consistent. Meters, meters, and meters. And we have a wavelength of 5.7 times 10 to the -7 meters. And as you notice, we have nanometers here. It's okay, we could have done millimeters if we wanted. It just make your units consistent, so the division you get meters over meters here, and your answer is going to be meters. If something was given in millimeters here, we could have done millimeters. Just keep them consistent, just so your math. That's why you always write your units. So that's problem 2. The third order dark fringe of 652 nanometers light is observed at an angle of 15 degrees when the light falls on 2 narrow slits. How far apart are the slits? So here we're given an angle, and we're also not looking to calculate the distance between nodal lines or destructive interference. Like in this question, we were looking at dark lines and delta x's, and as we said, it's hard to measure these dark ones with angles. But for this, we're not looking at that distance. we're not trying to use that at all. And so we can safely use this angle now, and we're also encouraged to since we're given it. So let's take a look at things. So third order dark fringe, what is that? That's n equals 3. That's the third nodal line, right? Dark fringe destructive interference of 652 nanometers. That's, we have a wavelength. And then an angle, we have a theta n here. And since it's the third order dark fringe, we can say it's the angle for the third nodal line. And we want to find out how far apart the slits are. So we have D. And so if we use the destructive angle formula, which was sine theta n minus half times lambda d, we have all the materials we need. So we just have to rearrange for d. And we get n minus half lambda over sine theta n. And we have n, lambda, and theta n. Plug in our values. We have only one unit to worry about, meters. And so it's going to come out meters and to a value of 6.30 times 10 to the negative 6. And so the distance between the two slits are 6.30 times 10 to the negative 6 meters. And so that's all for today.